3I Atlas may have formed 10 to 12 billion years ago, before the Sun existed. It crossed our solar system only once, moving too fast for the Sun to keep. And as it left forever, astronomers raced to read the chemical record inside its ice. This is Cosmion. Point it at any question in the universe, and it will show you the answer, whether you can bear it or not. Tonight, we follow that one-pass chase from a faint alert in Chile to the isotope measurements that point towards an ancient frozen birthplace. The alert arrived on the 1st of July 2025, when an Atlas survey telescope in Chile found a faint object moving against the stars. Older images showed the same object from at least mid-June. Because those earlier positions made the trail longer, they also changed the story. Instead of closing into an orbit around the Sun, the trail formed an open curve called a hyperbola. That open shape meant the object had arrived too fast for the Sun to capture. Only 2 confirmed interstellar objects had ever been seen before, so the newcomer became 3I Atlas, the third known visitor from beyond our solar system. It was already traveling at about 221,000 kilometers per hour, and although the Sun would pull it faster, the comet would remain at least 270 million kilometers from Earth, so none of that speed placed our planet in danger. Hubble could see the dust swelling around the nucleus, but not the solid body itself, which left its possible width somewhere between 440 meters and 5.6 kilometers, a range so wide that the smallest estimate could fit inside the largest more than 12 times. Astronomers therefore knew where the comet had come from before they knew how large it was. Its path was precise, while its body remained hidden. That open path turned an observation into a deadline, because 3I Atlas would pass through once and then continue into interstellar space without returning. Hubble, Webb, SPHEREx, and more than a dozen NASA assets joined the chase across the solar system. No single missed view could be allowed to erase the opportunity. The closest NASA images came from Mars, where the Mars Reconnaissance Orbiter watched from about 30 million kilometers away, and still the comet was only a small white smudge inside gas and dust, because even a planetary neighbor was not close enough to reveal the body beneath the coma. The JUICE spacecraft found another angle after the comet passed the Sun. Its large antenna, however, was facing forward as a heat shield rather than towards Earth. JUICE could observe, but it could not send the full result home. The measurements waited inside the spacecraft until 2 long downlinks finally carried them back. The comet kept moving. By then, the comet was months beyond its closest approach, yet the stored data showed a working coma and tail releasing about 2,000 kilograms of water vapor every second. That is roughly 70 Olympic swimming pools of water each day, which made 3I Atlas behave like a familiar comet under our Sun, even though its body and birth star stayed out of sight. If the nucleus would not reveal itself, the escaping gas might, because every molecule carried information about the ice from which it came. When 3I Atlas passed closest to the Sun on the 30th of October, 2025, it was still about 210 million kilometers away. Even there, sunlight was already changing it. Frozen material turned directly into gas and carried dust away, while SPHEREx found a coma dominated by carbon dioxide, with smaller amounts of carbon monoxide and water. And then, 2 months after closest approach, the comet brightened sharply, which suggested that the Sun's heat had taken time to reach material buried below the surface. Researchers think cosmic rays had processed the outer crust. Once the warmth pushed through that layer, protected water, rocky grains, and carbon-rich material began erupting into the coma. The surface had been misleading. Webb then detected methane around an interstellar visitor for the first time. but the timing mattered as much as the discovery itself. Methane escapes easily when it is near a warm surface, so its late arrival suggested that it had survived deeper inside, protected until the solar heat finally reached it. Webb also confirmed far more carbon dioxide than water, and although the comet cooled and its gas production fell in familiar ways, the proportions were unlike most comets formed here. The first interstellar visitor, Oumuamua, gave astronomers no measurable comet gas, while Borisov was too faint for work this detailed. 3I Atlas was different. Webb and the Very Large Telescope separated the light escaping from its coma into chemical fingerprints that allowed different molecules to be measured without ever seeing the nucleus directly. Inside those fingerprints were isotopes, which are versions of the same element with different weights, such as ordinary hydrogen and its heavier partner, deuterium. Those tiny differences matter because the balance between lighter and heavier forms changes with the environment. And once that balance is locked inside ice, it can survive as a record of formation. Webb found far more deuterium in the comet's water than astronomers usually measure in solar system comets. Even with one hydrogen replaced by deuterium, the molecule remains water. The measured proportion was about 30 times the solar system comet level reported by NASA. It was not a subtle difference. Carbon carried a second signal, and when the Very Large Telescope checked carbon and nitrogen inside cyanide gas, those independent ratios also stood apart from measurements of our comets. Different instruments had examined different molecules, yet the answers converged, pointing back towards the same kind of cold and chemically unfamiliar birthplace. The heavy water forms most easily in extreme cold, so the measured deuterium points to a region below about 30 Kelvin, where ice could keep its original balance. That is colder than minus 240 degrees Celsius, and once the ice formed there, it could not warm enough to erase the fingerprint we now measure. The carbon ratios added another constraint by pointing towards a metal poor environment, where metal is the astronomer's name for every element heavier than hydrogen and helium. Early stars formed before many generations of older stars had created and scattered those heavier elements, which meant their surrounding disks began with a different chemical mixture. Together, the measurements fit the cold outer disk around an old metal poor star, where an icy body could assemble far from its sun. The identity of that star remains unknown. As generations of stars lived and died, they slowly changed the isotope balance of the galaxy, so researchers used models of that chemical history to work backwards from the comet's measurements. Those models place the formation of its material around 10 to 12 billion years ago, compared with about 4.5 billion years for our own solar system. The Sun did not yet exist during the era suggested by the models. The ice inside 3I Atlas may therefore preserve a chapter of planet formation billions of years older than ours. That is the clue it carried across the dark. But this is where the story has to slow down, because 10 to 12 billion years is an inference from galactic chemistry, rather than a date measured directly inside the comet, and the distinction matters whenever a model reaches further back than any surviving observation can follow. The answer changes with assumptions about how quickly stars formed, how they altered the galaxy, and where the comet assembled, so the range carries genuine uncertainty. Even so, two isotope studies using different molecules agree on the direction of the result. 3I Atlas probably formed in colder and older surroundings than the comets born around our Sun. A formation age is not a travel time, however, because ancient material could remain beside its parent star for billions of years before an encounter finally threw it free. We therefore do not know which star lost it, when it escaped, or what caused the ejection. The chemistry narrows the kind of nursery, but it does not give us an address. Under our Sun, 3I Atlas released water, dust, and gas according to familiar comet physics, while the proportions hidden inside that material preserved the difference between its system and ours. That is what makes interstellar objects so valuable. Instead of sending a spacecraft across the space between stars, another planetary system delivers part of its planet-building material to us. Our comets preserve the formation of a solar system about 4.5 billion years old, but this visitor may preserve chemistry from a much earlier generation of worlds. 3I Atlas is now traveling outward on the same open path that revealed its origin, and although the Sun will slow it, nothing here can turn it around. There will be no second close pass, so every spectrum gathered during this brief campaign has become part of a permanent record that cannot be collected again. That chance is gone. For a short time, telescopes across our solar system became a laboratory for matter formed around another star, and the sample arrived without any mission crossing interstellar space. We may never learn where 3I Atlas began, but its ice still carries evidence that cold worlds were forming when the Milky Way was young. Subscribe to Cosmion. The next interstellar visitor will not wait for us.